Hello people, welcome to Gurukula. I am Jai. So today in this video we will be talking about the distance vector algorithm and then the routing information protocol. So without any further delay, let's get into the topic. In our previous video, we have spoke about the difference between algorithm and then the protocol, and then we have seen what are all the basic assumptions that we need to do for understanding the concepts of routing, and then we have majorly seen what are all the various classifications that is available in the routing algorithms. So just to recap, and this is what the basic types of routing protocols that we have. So just to recap, the routing protocols are classified into interior gateway protocols and then the exterior gateway protocols. And whereas interior gateway protocols are further classified into distance vector algorithm and then the link state algorithm. And whereas exterior gateway protocols will have path vector algorithm. And in our subsequent videos, we will be talking about these three algorithms in detail. And this video is more about distance vector routing algorithm and its associated protocol. So distance vector routing algorithm comes with a protocol called RIP, so that is routing information protocol, and link state algorithm is associated with OSPF protocol, and path vector algorithm is associated with BGP protocol. So this is what will be the next subsequent videos that we will be discussing here in our module of computer networks. So as we get into distance vector algorithm, so the distance vector algorithm means that the routes are advertised by providing two important characteristics. The first one will be the distance and then the second one will be the vector. So distance is nothing but it is how far the destination is. So this distance can be computed using several metrics such as hop count, cost, bandwidth, delay, etc. And whereas vector is an another parameter that we will be using in order to compute the routing table of any particular router, whereas the vector represents the direction of the next hop which will lead us to reach the destination. So there are two important parameters which we need to keep in mind. The first one is the distance and the second one is the vector. So distance is how far we need to travel to reach the destination, and vector is in which direction we need to travel in order to reach the destination. So these are all the two parameters that we will be taking care of while computing the distance vector algorithm. So now we will get deeper into the distance vector algorithm. The idea behind the distance vector routing is that it maintains a table with the distance to every node. So each and every node will have a table where the distance to each and every node will be maintained over here. So as this is what the simple example we could take in mind. So we can see that this will be the total distance or the cost we will be considering, and we will be entering into the routing table. So there are few basic assumptions that we need to make. So each node contains the cost of the link to the another node, and these costs are generally configured by the administrator. And the second assumption what we make over here is the link which is actually down due to some problem will be assigned with infinite costs. So why do we assign infinite cost? Because the router will always take the route which has the lowest cost. And remember, the term cost represents to the number of hops. So lesser the number of hops, so faster you can reach. So we will be always choosing the shortest path to reach from source to destination. So this is the reason why we always assign the infinite cost, which means the highest cost, which the router will never take that into account for reaching the destination. And this is how a typical network will look like, for which we will be computing the distance vector algorithm. So as already said, the circles whatever is represented over here represents the, see, all the circles that is represented like this represents the node, and the node can be anything. It can be a network, it can be a router, or it is any device that is connected onto the network. And the line which connects these two circles is what we call it as the link, which can be Ethernet cable or a Wi-Fi connection. It can be a wired connection or a wireless connection which connects these two nodes. And the numbers that is represented over here, that represents the actual cost. And here in our discussion, in most of the cases, the cost will be the number of hops. So all these have been explained already in the previous video. In case if you have missed the previous video, I will leave the link in the I button and as well as in the description section. So please do check the previous video so that you will have a better understanding of what we are discussing now. So getting into the actual computation process of distance vector routing, there are actually three stages which we need to come across in order to compute the routing table. So the first stage is initialization, and the second stage is sharing, and the last stage is updating others. So these three stages will be performed by each and every node in the network in order to compute the final routing table. So first let us see what happens in the initialization, and let us consider this is the given example network. So as given in the example network, we could see that there are 5 nodes named as A, B, C, D and E. And then all these nodes are connected via a link, and then each and every link has the costs. And now at initialization stage, each and every node will create an initialization table with the cost to reach all other nodes. So at an initialization stage, they do not know about all the nodes, because as you could see, there are few nodes that are directly connected and there are few nodes which are not directly connected to few nodes. For an example, to make it very clear, when you take node A is directly connected to node D, node C and as well as node B. Node A does not know any information about node E at initialization stage. So this is what we are trying to drive here. So node A will create its initialization table with the information of the directly connected nodes only, not the indirectly connected nodes. So as you can see, this is what the initialization table, this is not actually the routing table, this is what we call it as the initialization table. This is what we call it as the initialization table, and the first column represents the destination, so where the node has to reach, and then the second node represents the cost. We very well know the cost represents the number of hops that we consider in this discussion, and the next node represents the next hop where my packet has to be routed in order to reach the destination. So these are all the three important columns that will be there in the routing table, and the routing table will be maintained by the routers. So as of now, we could see that there are 5 destinations available in the network, and A can reach A with the cost of 0, which is nothing but A can reach A. So this is a self node. The packet need not go outside the node, so that the cost is actually 0. And then for reaching node B, so A can reach B with the cost of 5. So A can reach B. So actually you can see here, A can reach B. The cost is 5. And since A and B are directly connected node, we make it as hyphen. Though this hyphen represents it is a directly connected node. So B is a directly connected node to A, and A can reach C with a cost of 2, and that can be depicted in the figure. So A can reach C with a cost of 2. Similarly, A can reach D with the cost of 3. So we could see all these things in the figure, and we could also observe that A could not reach E, at least at the initialization stage. So A do not know how to reach E because it has not yet calculated the shortest path to reach the destination E node. So as of now, as of initialization stage, the cost to reach E is mentioned as infinite, which means that at this stage A cannot reach E. So that is what the meaning for this infinity. And the same principle will be applied for all other remaining nodes in the network, and this initialization table will be created at each and every node. So let's disclose the initialization table of node B. The same explanation remains as such. And similarly, each and every node will create its own initialization table. So I need not explain each and every table again and again, but whereas you can recap this explanation and you can apply on any other node so that you will get a better understanding of this initialization stage. So at an outset, initialization stage, each and every node will create its own initialization table, and this initialization table will have the details of the directly connected nodes alone. So that is what will be happening in the initialization stage. So now, once each and every node have created its own initialization table, then the process will be forwarded to the next stage, and the next stage will be the sharing. So what happens here in sharing? So from the given network, we can see that the node A do not know about node E, which we already know. By looking into the network, the initialization table, node A does not know about how to reach node E, and that is what mentioned over here. But who knows how to reach E? So node C knows how to reach E. As you can see, this is what the C's routing table, and the C actually knows how to reach E, and then E can be reached via B also, and similarly, and what? So this is how A can reach E. So A can reach E through B or through C. Yeah, so either A can reach E via B. So the route can be A to B and then B to E. This is one option that we can take, or the another option is A can reach E through C. This is what the another way, right? So how does A comes to know about there is a route present to E via B and C? So how does A comes to know about it? And that is what will be happening in the sharing stage. So in sharing stage, each and every node will exchange their initialization table with the neighboring nodes, meaning A will send its initialization table, and this is what the initialization table of A, and this copy of table will be sent to its directly connected node. So A will be sending A will be sending its initialization table to B, to C, and to D, because B, C, and D are the directly connected nodes for A. And based on that, B will be updating its own values, C will be updating its own values. So this exchange will happen several times. Each and every time a node updates its value, it will be sending its table to its neighboring node. So just to keep it simple and to understand what is happening in the updating stage, we will just consider the exchange between A and C alone. So we will see what happens if A sends its data to C and C sends its data to A. So similarly, node C do not know about how to reach node D. Yes, that is what depicted in the figure, and C does not know how to reach node D, but A knows how to reach node D. So while understanding the exchange and updating process that is happening between A and C, the same principle is applied for all the remaining update and exchanges happening in the network. So thus by sharing, node A can share its table to node C, so that C will come to know about the route that is available to reach node D via node A. And similarly, while receiving a updation table from C, node A will come to know about the route which can be reached to node E. So now let us see how the updating table will look like, and here each and every node in the network updates its own table from the table received from the neighboring nodes. So in our example, we will be talking about what happens, how A modifies its table based on the information received from C. So just for the reference, this is what will be the initialization table that A has received from C. So C has sent its initialization table to A, and now we will see how A is updating its table. So updating process will be happening in 3 steps. So the first step is the receiving node. In our case, the receiving node is A and the sending node is C. Please keep in mind, in our case, A is receiving the updation table from C and A is going to update the table. And the first step that we have to do is we need to make the changes in the cost column. So what we have to do in the cost column, since the table is received from C, we need to add the cost between the receiving node and then the sending node. And as you can see in the figure, the cost between A and C is 2. So we need to add the cost of 2 for each and every entry in the table that is received from C. This is what the table that we have received, and we need to add the cost of 2. Why 2? Because we are receiving this table from C and the cost between A and C is 2. So that is why we are adding 2 here. So once we add 2 here, A can reach A with the cost of 4. That is what mentioned as 4 here. And then B can be reached with the cost of 4 plus 2 is 6. So and 6 is what mentioned over here. And similarly 0 plus 2 is 2. And infinity plus 2 is again infinity. And 4 plus 2 is 6. And this is what the first step that we need to do. So this table is what we received, and A has created, or we can say that it has modified some content that is received based on the content that is received from C. And the next step is the receiving node have to add the name of the sending node to each row as the third column. So as you can see, the third column is the next node, and this is what we received from C. This is what the actual table what we received from C, and we can see that there are directly connected nodes available here. So A has to modify. The second step what we have to do is, this is what the first step, we have modified the cost, and we are now modifying the next node column. The next node column should be replaced with the receiving node value, because we are updating the data based on the information given from the sending node. So here the sending node is C, so that we are changing the column as C here. Now we can say that this is the A's modified table. And while completing these two stages, we will be having the modified table here, and this is what the modified table is. And then we have to go for the next step. And what's the next step? The receiving node compares each and every row. So now you have two copies of table at node A. One is A's old table, which is what you already had, this is what created during the initialization stage. And now after sharing an updation, you have an modified table. So you have to compare this table with this table, and then you have to create a final table like this. Now we can compare each and every row. So now as you can see, and this is what the step 3 is, while completing step 3, you will be comparing these two tables. So how to compare? So the destination is A. A can reach A with a cost of 4 via C. This is what the first entry says. But already in the previous table, A can reach A with a cost of 0. So the entry with the lowest cost will always be selected. So considering this in mind, when comparing these two entries, this entry is a better entry because we have the lowest cost here. And then checking for the second one, A can reach B with a cost of 6 if we go via C. But as of previous entry, we have A can reach B with a cost of 5, and it is a directly connected node. So comparing the cost, this is what the minimum cost is, so we will be taking this entry. And A can reach C with the cost of 2, and when there is a tie, as you can see, there is a tie over here because the cost is equal in both the cases. In case if you have a tie, then the old value is maintained in the final value. So here we can say that the final value is maintained this. And earlier, and then A cannot reach D via C, but we have already entry here. So comparing these two values, infinity is higher than 3, so that the lowest value 3 will be selected. And then finally here you have 6, and then here you have infinity. So when comparing these two values, infinity is the higher value, so that we will always choose the lowest value. We will choose 6 over here. So here the entries whatever been marked as tick mark, that will be the final entry. So this will be the A's new table. Now by observing A's news table, we can see that A has learned how to reach E. So now earlier A does not know how to reach node E. As you can see, there is an infinite symbol over here, which means that A cannot reach node E. Now, after getting and updating its table from C, A now knows how to reach E via C. So there is a path from C to reach E. So that is what will be happening in the updation stage. Alright, so just to sum up, there are just only three steps that you need to follow. The first step is you need to add the cost. The first step is you need to add the cost between A and C. Why A and C? Because we are discussing between what is happening between A and C. So A is the receiving node and C is the sending node. So you need to add the cost between the sending node and then the receiving node. Here in our case it is 2. So that is why you have added 2 in all the rows, and 2 plus 2 is 4, and that gives you the updated cost column. And the second step what you have to do is you need to create the updated next hop column, and the next hop column you need to simply replace the values of the receiving node, so sending node. So here the sending node is C, so that is why we have replaced all the values over C. So this two steps will give you the modified table. And then the third step is you need to compare the modified table versus the old table, and you need to always choose the lowest cost entries. So this is what the outset or the summary of the three steps that you need to perform in the updating stage. So that completes the updating stage. And several sharing will happen. We cannot say that this is what will be the only sharing that is available. So once A has updated its table, it is going to share its table again with B, C and D. Fine. So similarly, if B updates its table, it will send its updated table to A, C and D. Sorry, A, C and E. So likewise, several sharing will be happening between each and every nodes that is available in the network. And finally, the routing table will look like this. So we can see that A has completed the table, and one more thing what we have to observe here in the final converged routing table is no nodes is having the value of infinity. Now we can say that each and every node has the information, or it knows how to reach the other nodes in the network, which means that one node in the network can able to share its information with the remaining nodes in the network, which is a primary requirement of a network, right? So this is how the lowest cost will be created. So there is no infinity in any of the tables mentioned over here, which means that this happens after several exchanges that has happened. So now comes the question, when should I update something? So there are two types of updates that is available. So one is the periodic update, and in this periodic update each nodes will send its routing information with the neighboring nodes on regular intervals of time. Normally it is 30 seconds, and please to remember that this 30 seconds is not a standard one, and this will be varied depending upon the protocol that we use. And at least for routing information protocol we will be updating for every 30 seconds, and for the other protocols the period of time will be varying. And the second method of update is triggered update. So here in this particular approach, a node will be sharing the routing information only if there is any change in the routing table. In case if there is any change, the node will be sending its information to the neighboring nodes. Otherwise it will not be sending its routing table. So this can appear in two instances: when a node updates its table and entries are changed after updating. In our previous slide we might have discussing that what happens when C is sending its information to A. So based on C information, A has updated its own entry. So the entry for the last row has been changed. So in this case, A will be sharing its routing table with the remaining nodes in the network. And similarly, the other instances could be a node may detect any failure in the network, so that the cost to that particular node has to be changed to infinity, because that node has become unreachable. So that any node which is unreachable has to be changed to infinity. So now we will talk about the various problems that is available in distance vector routing. So generally there are high possibilities of a network to become unstable when we especially use distance vector algorithm. So we could put those problems as two types. One is two node instability problem and another one is three node instability problem. So here in two node instability problem, we can understand the problem of instability by considering this particular scenario. As you can see, this is what the example scenario that we are taking. So this is what the simple network, we have node X, we have node A and we have node B, and then the complete routing table of A is not given. Just for the sake of understanding, only the required entries is given. So this is not the complete routing table of A and B, we are just taking only the required values to understand the two node instability problem. So with this node, let us try to understand what is two node instability problem is. So here A can reach X with the cost of 2 and it is a directly connected node. So that is what this routing table represents. Similarly, B can reach X with a cost of 6. Why is it 6? So B is not a directly connected node to X. So B is connected to X via A. So whenever B wants to send the data to X, it has to send via A. So the cost will be 4 plus 2. So that is why it is 4 plus 2 is 6. So B can reach X with the cost of 6 and it has to send its information via A. So that is what the routing table is. So with this information, let us see what happens if the link to this X got failure. So as you can observe here, the link got detached and there is some problem in the link that connects A and X. So now which means that A could not able to reach X. So now by knowing that A will update its initialization table or its routing table immediately that X cannot be reached. So as you can see, X has updated its table. Sorry, A has updated its table like X is not reachable. It has made the cost as infinity. But B still has this particular entry which is maintained as like in the previous step. Fine. Now if A send its table to B, then B will also update like X is unreachable. Fine. If in case if A sends its table first, then there is absolutely no problem. There is no chance of any instability problem if A sends its table first to B. Now, just in case, what happens if B sends its information to A before A is updating to B? Now, what happens is if B sends its table to A, now A will understand that there is some link which is actually connecting the node X via B. So, what happens is, see, the node A will update its table again. So, they can reach X with a cost of 10. How is this 10? B says that X can be reachable with a cost of 6. So B says X can be reached with a cost of 6. So as per updating procedure, you need to update, you need to add the cost between the sending node and then the receiving node. So 6 plus 4. So 6 plus 4 will be given. This 6 is this and this 4 is this. So when you add 6 and 4, you will get 10 in total. And as per updating procedure, the next hop column has to be updated based on the sending node. Here the sending node is B, so that the B is updated over here. So now A comes to know that X can be reached with a cost of 10 via B. So this is what the updated table will look like. And now we very well know that this table is actually the false entry and there is no such root here. So when this actually initiates the two node instability problem. So now when this table of exchange, then after A updates its table, A will send its table to B. Now B will update this information that okay fine. So A says since X is directly connected with A, any information that is received from A will be more reliable than my own information. Right? So X knows more about A. So A knows more about X. So B will update its information based on the X table. So it says that now it is 10. So here it is 10 and we need to add this 4 together. So 10 plus 4 will give you 14. And the next node, since A is the sending node here, we need to put A here. So B will update its table like, okay, X can be reached with a cost of 14 via A. And this exchanges will keep on happening after several stages. A and B will update that X has become unreachable and the infinity will be given over here. So the period during this time the network is unstable. A and B are keep on exchanging its value, and then it will take much more time to settle down, or in technical terms we can say that it will take much more time to converge, to get to know that X has been detached from the network. And this problem is what actually we call it as two node instability problem. And when there is a problem, obviously there will be the solution, and the solutions will be, the first one is, there are three remedies actually that we can do for coming out of two node instability problem. So the first one is defining the infinity. You can actually define the value of infinity. So higher the value of infinity, it will take larger time to converge. So it is always a better option to reduce the value for the infinity. Say for an example, in case of, say, if the node is not reachable after 30 hops, we can define this as infinity. Or in other case, we can say if the node is not reachable within 16 hops, we can define this as infinity. So we have to reduce the value over here. So this network will be converged faster rather than this particular network. So this is what the one remedy which we can do for coming out of two node instability problem. And the second one is going for the split horizon. So in this strategy, instead of flooding the table through the each and every interface that we have, each node sends only the parts of its routing table through each interface. So using the split horizon strategy, which has one drawback, which means that when the protocol is not hearing about something or some particular node for a period of time, it automatically deletes the entry from its routing table. In our previous example, if A is not listening about X for a more period of time, then A will automatically delete the entry X from its routing table. So that is what the split horizon is. So the split horizon is nothing but B will send only the partial table. Say for an example, to just to understand split horizon in detail, so we have A, we have B, and we have X here, and B's routing table will be like this. Okay, let us have one more node here. So we will have C and X in the B's routing table. So this is B's routing table. So as far as split horizon, instead of sending this entire routing table, so B can be reached C with the cost of 2. I will just fill out this routing table for understanding the concept very well. So this can be 2 and this can be 1. So that B can reach C with the cost of 2 and it is a directly connected node, and B can reach X with a cost of 3 via A. So this is what will be the information which has to be sent to A for updation, right? So what happens is, instead of sending this entire table, B will send only the parts of its table. It will send only the data, only the value about C. It will not send about X, because B came to know about X via A, right? So it is generally a common sense that A knows more about X rather than B knows. Fine. So there is no point of sending the same information again which A actually knows, because B updated the information about X via A. So wherever the next node A is available, this entries will not be sent to A. Fine. So it will send only the partial table. So this is what will be the sent as per split horizon technique. So if we follow split horizon technique, A is not going to listen about X from B over a period of time. So there is a lots of possibility that A can remove the entry of X from its routing table. So that is what is actually mentioned in split horizon. But there is one technology, or there is one remedy which could actually solve. So in Poisson reverse, what actually happens is, instead of not sending the entire table, we can send the table. So B will be sending its table like this. So this is B's table again. So B can reach C with the cost of 2 and it is directly connected node, and it is X, 3 and A. So this is what the actual table what B has. So instead of sending this as per Poisson reverse, what will happen is, the split horizon has to be implemented but with the Poisson reverse. So Poisson reverse is nothing but changing this 3 to infinity. So B will send its entire table, but it will actually poison the table. So it will not send the actual value 3, but instead of 3, it will send the value of infinity when it is sending its table to A only. because B came to know about X only through A, right? So this is what the technique, what we call it as split horizon with Poisson reverse. So this Poisson reverse is nothing but, in a general English word, we can say that do not use this value because what I know about this root comes from you. Alright, since B came to know about X via A, when B updates its table, this entry will be updated to infinity. So that A will not consider this particular entry, and at the same time, X will be heard by A for the regular period of time. So there is no possibility of removing this node from the network. So again, coming to the next type of instability, there is a 3-node instability problem, and the 3-node instability problem is again as similar problem to 2-node instability problem, but whereas here the involved node is 3 in number. So when there are more number of routes to reach a particular destination, as you can see, A can send its information to B via directly connected link, or A can send its information to B via C as well. So the communication between A and B has two links here. One is a directly connected link and another one is via C. In case if there are loops like this, then again this initiates the 3-node instability problem. So here in 3-node instability problem, as you can see, again the same scenario is maintained here. We have represented only the partial table, not the complete table. As like similarly, X lost its connection to X and this table has been updated over here. So X has become unreachable, and this updated table will be sent to both B and as well as C. Now, due to some network problem, the packet or the update which is sent to C has not reached C. This packet has been lost. So this packet has been lost. So what happened? Only B will be updating its table and C will not update its table. Now B will be sending its table and C will be exchanging its table. Again, this creates a 3-node instability problem. So this is what happens when B sends its routing table to A. So when B sends its routing table to A, now A will come to know that we can reach X with a cost of 8 plus 4. So it is updated as 12 here. And now when it is again getting updated, we can just update the table again. So A will come to know that okay, X can be reached via B. So this problem is what we call it as 3-node instability problem. So again, coming to the protocol that is associated to distance vector, we will be using the routing information protocol. So these are all the various assumptions and various considerations that what we will do in routing information protocol. So the first and foremost point that you need to keep in mind is RIP is an intra-domain routing protocol, not an inter-domain routing protocol. So already we have a clear discussion on what is intra-domain routing and what is inter-domain routing. So the link for the previous videos is always given on the I button. So please do check the previous videos for the detailed discussion on intra-domain and inter-domain routing protocols. And coming to the considerations, we need to keep in mind that only the routers will have the routing table, not the networks. And the first column always represents the network address, because the destination is always going to be the network where we are going to send some packets and not the routers. So that the destination address, which means the first column, is always the network address. And the metric what we used in our discussion is the hop count, and the infinity is again 16. As already said, generally the value will be 30, and since as far as routing information protocol, the default infinite value what we choose will be 16 seconds. And the node column defines the address of the router to reach the particular destination. So this can be more understood by looking into this real-time example scenario. So as you can see over here, the black color line represents the network, and then the R1, R2, R3 represents the routers, and the line, this line particularly represents the link that connects the network. So these are all the networks what we have. And as you can see, this network is represented by a network ID. So the router 2 table will have all the entries that is destinated to different network. So when we take this particular example, suppose this particular router R2 wants to send a particular data to this particular network. So 205.5.5.0. So 205.5.5.0 can be reached with 3 hops. So let us see how is this being done. In case if this particular network wants to send the data to this particular network, then the data will be forwarded to this particular interface, right? So 130.10.0.2. So this router only knows that any packet that is destinated to 5.5.0 has to be sent via this particular link. Now the packet will be sent. So this is where the first hop will be happening. So this is what the first hop is. So the packet will be sent from this to this. Once the packet has reached this particular router, and this particular router will search for the destination location, which is 205.5.5.0. So this particular router searches for 205.5.0, and this can be reached via this particular address. So 130.11.0.1. So this packet will be sending its information to this particular router by referring this particular table, and then this router will check the destination. So that's here it is 205.5.5.0, and this which has one hop, so which is a directly connected node, so it will be sent actually to this particular network. So when you observe the number of hops that it has taken, so here is the first hop, and here is the second hop, and here is the third hop. So that is what mentioned over here. You need to take 3 hops to reach the destination. So this is how the real-time environment or the real-time scenario will be. So that is all about in this particular video. We have seen a lot about the distance vector algorithm, and then the 3 stages of creating the routing table: initialization, sharing, and then updation. And we have also seen the 2-node instability problem and the remedies for coming out of this instability problem. And finally we have seen in real-time environment how the routing tables will look like in real-time scenarios. So that is all about this particular video, and I'm winding up the video here, and we are going to see you in the next video. Until then, it's bye from Jay and happy learning.